Hello everyone, I'm Vinicius Beber, a researcher from the Fraunhofer IFAM Institute in Bremen, Germany. And today I'd like to share with you the presentation TCD-based fatigue lifetime prediction of adhesively bonded joints, which is a research carried out in cooperation with my colleague Bernd Schneider. And I'd like to thank deeply Professor Taylor and Professor Susmel for their invitation to be part of the mini symposium on applications of the TCD. So the motivation behind this research is the use of structural adhesives. Structural adhesive bonding is a joining technology with growing application in several industries like aircraft industry, automotive industry, marine technology, and construction, many applications. One of the advantages of structural adhesive bonding is the possibility of multi-material joining, so combining different types of materials like composites and metals into a single structure, which sometimes is not possible with other joining technologies, which makes possible to construct structures with high stiffness and low weight, which leads to lightweight design that is very advantageous both in terms of reduction of emissions and reduction of fuel consumption, which is good both for the environment but also economically due to reduction of costs. And adhesively bonded structures are exposed to cyclic loads, for instance vibration, which make them suitable to fatigue. And fatigue is a major cause of mechanical failure for adhesively bonded structures. So given that fatigue is one of the major causes of mechanical failure of engineering structure, it is very important to be able to predict the fatigue lifetime. So for a given engineering structure subjected to a certain cyclic load, the objective is to choose or to find a prediction method that for a given cyclic load and a given geometry to be able to predict the fatigue lifetime or the number of cycles to failure. Another very important motivation for this investigation is the existence of stress concentrations. In many engineering structures that are bonded at certain regions, for instance at overlap ends, and also by hybrid joints close to the rivet or close to a bolt, you will find stress concentrations, and they cause local stress rates, a triaxial stress state, and they are a spot for crack initiation. However, it's very hard to isolate the stress concentration effect with bonded joints due to the existence of adhesion and also the mechanical response of the adherent. So in a way to isolate or to study it more easily, we can use notched bulk specimens, which are pure adhesive specimens with a notch, could be internal or external, that will replicate this stress concentration, but with pure adhesive, which makes it easier to study it afterwards. In this study case, we use two different types of structural adhesives. Both of them are toughened epoxies, so they're an epoxy matrix toughened with particles. Both adhesives are single component. Here we describe the two types of adhesives. One is called RBT, which is toughened with rubber and has a hot cure. And the second one we will call PUT. It's a polyurethane toughened epoxy, also with hot cure. Here on the right side, you can see the different stress strain curves of both adhesives. So the PUT adhesive is slightly more stiff, so has a Young's module of 2000, and the RBT has a Young's module of 1600. The RBT adhesive is much more plastically deformable, so with an elongation at break of 15.5 versus 7.5 of the PUT adhesive. and they have quite similar tensile strength, so in the around 33-34 megapascal. Regarding now the numerical approach for the simulation, we used an elastoplastic material model. We use this due to experimental indication of a plastic zone, so whitening, as you see here in the quasi-static test, the presence of whitening of both types of samples. And we use a linear Drucker Prager model for the material, since adhesives show hydrostatic stress dependence on their yielding behavior, and many studies have shown that this is a suitable approach for structural adhesives. So if you compare with the Vomices material model, you can see here, if by plotting the hydrostatic pressure, hydrostatic stress and the Vomices stress, you see that the difference between the linear Drucker Prager model and a Vomices material model. For the lifetime prediction, the method was defined as shown here. So we use the stress life approach, which requires stress calculation, in this case using finite element analysis, and an SN curve, which is obtained experimentally. It has a straightforward application and has been proven suitable for adhesives in many projects. And a reference SN curve is necessary. This reference SN curves shows the relation between fatigue strength and fatigue lifetime. Equivalent stress is necessary because different types of samples will have a different types of stresses, and the use of the nominal stress approach is not enough for compare two different types of samples. And a method must be chosen to address the stress inhomogeneity, because as you can see here in the right hand side, when you have a stress concentration, you have a distribution of stress. So from this stress distribution, one single effective stress must be taken out to represent well this stress distribution. And once again, the question that we want to answer is, given a particular force amplitude, which is the fatigue lifetime. So now the method parameters. Two equivalent stresses were used in this investigation. One is the Drucker Prager equivalent stress, which has is hydrostatic stress dependent. So it has a component of the Vomices stress, but also has a dependence on the hydrostatic stress, and the max principal stress, which is hydrostatic stress independent, which is the maximum value of the principal stresses. To obtain the effective stress, the theory of critical distance was used. It has been shown valid for adhesives and fatigue in many applications, and is based in a parameter, the critical distance. And here we use both approaches, the point method and the line method. The point method, giving the stress distribution, you take the value of the effective stress from a distance from the critical distance, and using the line method, we take the effective stress as the integration of the stress for 2 times the critical distance. Well, one of the main challenges in the use of the TCD for adhesively bonded joints is the determination of the critical distance, so which value of the critical distance to take. In this work, we used a calibration method, which was used for adhesives, for quasi-static predictions. And the idea is that for the same effective stress, you have the same fatigue lifetime. So the idea is to take 2 samples at the same fatigue lifetime, as you can see here, 2 notches, one with internal notch, one with external notch. Although they have different nominal SN curves, by taking a point with the same fatigue lifetime and plotting the distribution of equivalent stress amplitude, and taking the same point, the point where this curve crosses, this is the point where theoretically they have the same effective stress. This crossing point is the critical distance. In this case, for both adhesives, the critical distance in millimeters was 0.1 millimeter. Then the process of lifetime prediction was done as follows. So considering the sample to be predicted, which is subjected to a certain force, by having chosen prior the equivalent stress at the critical distance, you have the effective stress. Then, having a reference sample, which has a much easier geometry, in the finite element analysis, you would increase the force, this external force, until the same value of critical distance was obtained in the reference sample. Then, taking the reference sample in the SN curve, you'd be able to predict the lifetime of your sample to be predicted. The validation of this method was done considering 2 types of adhesives and 3 types of samples with 3 different types of notches, an internal notch of 2 millimeters and external notches with 0.5 and 0.3 millimeters. They have different highly stressed regions, and also they have different stress concentration factors, trying to predict fatigue lifetimes of 1,000, 10,000, 100,000, 1 million cycles using as reference SN curve an internal notched sample with a 1 millimeter. In this case, we use as accuracy assessment the error factor, which is basically the factor of your accuracy. For instance, if you have experimental lifetime of 10,000 and your prediction was 12,000, then your error factor would be 2. Or if you have experimental lifetime of 200,000 and then you predict 600,000, your error factor is 3. And comparing the predicted lifetimes and the experimental lifetime. Here you can see the prediction accuracy using the max principal stress as equivalent stress and the Drucker Prager as equivalent stress for both RBT adhesive and PUT adhesive. By looking at the equivalent stress, the Drucker Prager equivalent stress has a high accuracy. As you can see here, the relative factor error of the purple curves is much smaller than the orange curves. Regarding the adhesives, the PUT adhesive, we had a higher accuracy with the PUT adhesive, and regarding the TCD method, point method or line method, for the max principal stress, it was better with the point method, and for the Drucker Prager stress, there is no clear trend. But it's important to highlight that by using the Drucker Prager equivalent stress, we had a suitable accuracy for industrial applications, which for adhesives, it's around 5 to 8. A factor of 5 to 8 is good. And this was obtained for both adhesives and all types of samples. Now to summarize some of the results that we had here regarding the use of TCD for structure adhesive. TCD is a very efficient technique for lifetime prediction of structure adhesives. We had a very good accuracy for different types of samples and both types of adhesives. However, the current challenge is the determination of the critical distance. A method was proposed here. Nonetheless, some results have suggested that the critical distance might be dependent on the type of joint. So for other projects that we used, this still needs verification, and the TCD still needs to be validated under other conditions, for instance, fatigue with phase shift, fatigue with variable mean load, and etc. Finally, I would like to acknowledge the financial support of the Science Without Borders program and the coordination of improvement of higher education personnel, the FAT, and the FOSTA for the financial support of the projects which were shown here. And finally, thank you very much for your attention and your interest on this research, and we hope we have time to discuss it online. Thanks a lot.